Hey everyone, welcome to episode 3 of Everyday Physics. Today we're going to be looking at circular motion with a bucket of water. Alright, so I got this bucket here rigged up to some rope. We're going to take some water. I'm going to pick up this bucket and we're going to start swinging it in a circle. Ready? All right, we got take 2. We got a new bucket here, hopefully a little bit more sturdy than the last one. Let's give it a whirl. We'll use numbers from take 2. So the mass of the water was about 2.9 kilograms. The radius between where I was holding it and the center of mass of the water is about 0.9 meters. And then the average velocity as it goes around is about 3.2 meters per second. And I just found that by circumference over the time it took to do one circle. The velocity doesn't stay constant the entire time, and we'll talk more about that later, but for the purposes of starting off, the average velocity works just fine. So I drew these pictures, and the first thing that we're going to want to do is make a force diagram for when it's at the bottom and when it's at the top of the circle. So obviously in both cases we're going to have the force of gravity pointing down. And now remember, when things are moving in a circle, there has to be a force towards the center of the circle. When it's at the bottom, the normal force from the bucket on the water points up, and this force is significantly bigger than the force of gravity. When it's at the top, the normal force from the bucket points down. Now this confuses a lot of people because it seems like, well, if there's a force pointing down, wouldn't the water come out of the bucket? But it's actually the opposite. The bucket pushes down on the water while the water pushes up on the bucket. And the velocity in the meantime is this direction, and the force is this direction, causing it to make a circle. So now we'll start off by calculating some forces using the equation for circular motion, that is the sum of the unbalanced force over the mass equals v squared over r. When the water's at the bottom of the circle, the normal force is significantly bigger than the force of gravity, and the net force is upwards. We can express the sum of the forces as the normal force minus the gravitational force, since they're in opposite directions. When we look at it at the top, both the gravitational force and the normal force point in the same direction, downwards, towards the center of the circle. So in this case, we can write the sum of the forces as Fn plus Fg. All right, first we'll solve for the normal force when the bucket is at the bottom of the circle. So we know the normal force is bigger than gravity and they point in opposite directions. So again, we'll give the sum of the forces as the normal force minus the gravitational force. Next, we can do some algebraic manipulation, move the mass over and then add Fg. And then we can plug in the numbers that we know. So the 2.9 for the mass, 3.2 for the average velocity, 0.9 for the radius. And then we find that the normal force when it's at the bottom is 61 newtons. This is 61. And for comparison, the gravitational force is 28 newtons, pointing downwards. Now we can solve for the normal force when it's at the top. Again, in this case, the forces are in the same direction, so the sum is just going to be Fn plus Fg. We'll do the same algebra as before, except this time this is a minus sign here. And then we can find that it's 4.6 newtons of normal force when it's at the top. Now, regardless of where it is, top or bottom, the sum of the forces is 33 newtons the entire time. The normal force changes, the gravity stays constant, and the total stays constant at 33. It's just the directions that change. So now we can see that the acceleration into the center of the circle at all times, the sum of the forces over the mass, is 11.4 meters per second squared. The other thing we know about circular motion is that objects usually have to have some sort of minimum velocity for them to continue moving in a circle. So let's examine our original equation for when it's at the top. So we have the sum of the forces as the normal force plus the gravitational force. The gravitational force is constant regardless of what happens, it's just m times g, and the mass is staying the same. The normal force can change, and that's dependent on how fast the bucket's moving. The faster it's moving, the more force the bucket will exert on the water. So to find the minimum possible velocity that we can do with this bucket and to continue moving in a circle, we have to set the normal force equal to 0. So in that case, the gravitational force would be the only force. And if we solve this out, we get that the minimum velocity is the square root of r times g, or 2.97 meters per second for this scenario. And I was moving it at about 3 point something, so if I had gone just a little bit slower, it wouldn't have stayed moving in a circle. There's one last thing I want to talk about, and that's that the velocity isn't actually constant when it's moving around the circle. And you might have noticed this when you were looking at it, that it seems like it whips around the bottom a lot faster than it goes around the top. So if we make little pictures of when it's on the sides of its circle, and we make force diagrams, we notice that the normal force from the bucket on the water is obviously towards the center of the circle, but when it's coming down, the gravitational force downwards points in the same direction as the velocity. And we know from kinematics that that just means it's speeding up. When it's going up around the circle, again, normal force towards the center, but the gravitational force is pointing down while the velocity's up, opposite direction, just means it's slowing down. The other way you can look at this is that when it's at the bottom, it has less gravitational potential energy and more kinetic energy than when it's at the top. Now, if you wanted to, you could do the math and figure out exactly what the velocities were at the top and bottom. You'd have to use energy, gravitational potential, and kinetic. For the purposes of this video, I'm not going to. I think the average velocity is a good enough approximation for both spots that it works. Thanks for watching episode 3. Hopefully you learned something, and hopefully you enjoyed watching me getting soaked. If you want to do this lab at home, you can. Just proceed with caution, and have a good day.